Hello everyone. It's our pleasure to have Yanming here, to present his work in our seminar. Today he will share with us about how can we learn the properties of quantum learning body states using machine learning algorithm efficiently and with some provable guarantees. So Yanming, you can the floor is yours and you can start your presentation. Thanks.
Okay. Good afternoon, everyone. First, I'd like to thank the organizer for inviting me. It's a great pleasure for me to be here sharing our recent work on exponentially improved efficient machine learning for quantum many-body states with provable guarantees. And for many details of this talk, you can find in our recent archive paper here and MOIC. And this work was collaborated with Clem's G19 and Frank Norrie from University of Michigan and RIKEN. As you can see, this talk will be covered by roughly 8 parts. And let me just start from the introduction. And we know that predicting quantum many-body ground state and their properties is at the heart of a multitude of branches modern quantum science, from condensed matter physics, quantum simulation, to quantum chemistry. But finding the exact ground state of quantum many-body Hamiltonians is generically beyond the reach of efficient classical algorithms. If you assume, or if under a widely believed conjecture that in computational complexity theory that the P is not equal to NP, because the Hilbert space of many-body quantum system is exponentially large. And so such complexity arises from the rich structure of the Hilbert space of quantum many-body systems and the principles of quantum mechanics. Also, it has been shown that for a particular family of gate Hamiltonians in 2 dimensions, evaluating the ground state properties such as expectations of some local operators can be as hard as solving. I explicitly a reference here, but if you read our paper, you can find many relevant references in each items. On the other hand, machine learning recently has been a hot topic, which is an effective approximation scheme whose solution can be efficiently obtained via some optimization processes. It has found a wide spectrum of applications in solving complex quantum physics problems, for example, predicting the quantum states and identifying physics and phase transitions. This may raise the hope that machine learning may also help in some cases with efficiently predicting the quantum many-body ground state and their properties. For example, when the Hamiltonian is depends on parameters and the training set of ground state or the ground state properties can be efficiently prepared for some specific choice of parameters. In which case, the learning algorithms can help to generalize to arbitrary parameters with a lower cost compared to that required experiments, and to make predictions and also cover the entire parameter space. Usually, it was done within the same quantum phase. If we assume the state is continuous or it's smooth, then the predicted states or the properties can be very close to the true values, up to a small prediction error, epsilon. Such a situation has recently been addressed by this paper in Caltech group, from John Fresco's group in Caltech, and it's a very good paper, and they obtained a rigorous guarantee for learning and predicting properties of quantum many-body ground states, provided that the training set of the ground state is efficiently available via classical shadow tomography. Sorry, I have to. there is some Wi-Fi problem, and let me just fix it. I think it's quick.
Yeah, no worries.
Can you hear my voice? Some problem.
Yeah, can hear you, but it's a bit laggy. Can you are muted? Yeah, can you unmute yourself?
Okay, I'm sorry, it's a bit communication breakdown.
Okay, no worries.
No, can you hear my voice?
Yeah, can hear your voice. But you haven't share your screen.
The network is a bit problematic here. Sorry.
Mm-hmm.
Let's just continue. Now it's okay, right? It's clear.
Yes, that's good.
So yeah, in this paper, the Caltech group they give a rigorous guarantee for learning and prediction properties of the metabolic ground state if given a training set for different parameters, and the state was obtained by classical shadow tomography, for example. But there was a bit unfortunate that they found the number of samples required is exponentially dependent on the inverse prediction error epsilon, and they found that this was universal for generic gapped Hamiltonians. Here, M is the dimension of the parameter space. This result can be very useful when M is a large number and we are focusing on the scaling of the dimension, but the error tolerance can be high and the precise predictions are not in focus. So another relevant practice scenario could be that the scaling of the number of samples with accuracy is a main concern, where the dimension of the parameter space is a finite constant. So in our work, we are motivated by the framework of the so-called PAC learnable, which is a fundamental theory of computational learning and which requires the minimum number of samples for the learning task to be polynomially the inverse of the prediction error and the inverse of the failure probability delta. So this I think is a very famous framework for computational learning. And if the number of samples is a polynomial function of such quantities, they call the concept class is PAC learnable. So also inspired by this, we explore theoretical guarantees for polynomially efficient learning that may significantly reduce the exponential scaling number of samples in this paper. So we hope to find a decrease of many orders of magnitude in sample complexity. And finally, we will give a demonstration with a simple model. It's called the one-dimensional transverse field IC model. We assume a pairwise family of quantum many-body Hamiltonians with ground status denoted by rho, and where it's a parameterized by some physical parameters. The parameter space is given by chi. It's actually an m-dimensional cubic of length L in each dimension. And we further assume the parameter space is equipped with a probability measure mu, according to which the sample xi is drawn from the parameter space. And the training set is the ground state xi and rho as a function of xi of size n can be efficiently prepared. For preparing the state, usually one uses the state tomography, quantum state tomography for accessing rho, but experimentally it's generally expensive for multi-qubit systems. So there are already various strategies proposed to reduce the cost of quantum state tomography. For example, using compressed sensing, neural network state tomography, and classical shadow tomography. In classical shadow tomography, the state is approximated by classical measurements, the T-randomized polymeasurements, and under locality assumptions, they have showed the approximation where the shadow states have been proved to be very efficient, require only such a complexity copies of measurements. Here, n is the number of qubits, and epsilon is the precision of tomography trace-law. Our work mainly assume it's very general, and we only assume the target function is continuous. We only, for example, within the same quantum phase or other cases, but we only assume the learning target function to be continuous functions. And given a set of training set, xi, rho, for arbitrary parameter in the parameter space, we can construct such a predictor for the density matrix. It's actually like what we have done in the kernel regression, and but in that case, usually the rho is a continuous function. I think in the Prensco's group in the science paper, they first proposed such a form to predict the density matrix. But here they use the classical shadow tomography, approximated states. And also further, if we assume the kernels with translational symmetry and is parameterized by lambda, the parameter usually is an integer. So the one key point actually pointed by Clemens was pointed by Clemens that in this protocol of kernel regression, we have to, because sigma n is a predicted density operator, so we have to preserve the fundamental properties of the density matrix for all parameters. That's to say, it should be Hermitian, positive, semi-definite, and have trace one. So the first two conditions require the kernel function to be positive and a real number, whereas the last one, trace one, can be approximately satisfied, because here xi are samples randomly drawn from the parameter space according to some probability measure. So there can be statistical fluctuations and errors. So the trace can be approximately preserved to one. Under this constraint, and we proposed to use the so-called positive good kernels, PGKs, to satisfy the physical requirements. The first condition for the PGK is the positivity and boundedness, which requires the kernel function to be a positive real number, and the order at the most increase at the order of lambda tau. I mean, tau is some positive integer. And the second, this should be normalized with respect to the probability measure mu. And the third is called the eta. We call it eta convergence. For arbitrary positive number eta, the absolute integration away from this eta should be 0. Actually, such concept was not first introduced by us. It's actually already in mathematical analysis or Fourier analysis, where approximating some continuous functions use kernel convolutions. We just introduced them to here to learn the for the problem learning density matrix. And in the usual definition of good kernels in mathematical analysis, there is no positivity and boundedness requirement. But here, the normalization and the interconvergence were already there. And the first requirement was L1 boundedness. So the L1 norm of the kernel should be bounded by some constant when lambda is tends to infinity. But here we can, if we combine the positivity and the normalization condition, it can be automatically satisfied for the L1 boundedness. L1 norm is actually equals to 1 exactly here. So as an example, we present a rectangular fair kernel, which is actually can be shown to be a PGK and given by the product of this factor in m dimensions. So m is the dimension of the parameter space, and L, as I mentioned earlier, is the length of the parameter space in each dimension. Lambda is the integer here. It's a parameter of the kernel. And I'd like to talk more about the connection to physical properties of the positive good kernels. And the normalization of the kernel can guarantee that the trace of the predicted density matrix is approximate to 1 with high probability. And the three conditions totally combines to allow the convolution of a continuous quantum state with such PGKs to approximate the state itself within a prescribed precision. And in the science paper, the authors used the L2 Dirichlet kernel to obtain a rigorous guarantee. And we find this kernel can fail to be a PGK. In one sense, it's, for example, if we take the one dimension, the entries of the Dirichlet kernel can be negative for some values of x, so it's not always positive. And also, the L1 norm of the kernel is not upper bounded by a constant when lambda is a large number. So it violates the positivity and the L1 boundedness. With the PGK regression, here we come to the theory 1 of our work. If we are given a family of n-qubit Hamiltonians defined on the parameter space, as mentioned earlier, and if we further assume the continuous entries on this parameter space, and the training set consists of xi and the real xi of size n can be available, where xi is drawn from the parameter space according to a probability measure. Then our purpose is to predict the density matrix sigma n as provided in equation 1 and given by the PGKs to be close to the true ground state for arbitrary parameter in terms of prediction error here. Here the prediction error we use this of the predicted density matrix should be close to 1 up to epsilon error at the same time. Is it okay?
It's actually a bit laggy on your side. Maybe if you want, you can turn off the cameras to kind of increase the bandwidth a bit.
Unstable?
Yeah, as in on my side is just a bit unstable. I'm not too sure about for others. I guess you can like turn off your camera so that you can have more bandwidth to connect to.
So if your side is unstable, you can try to stop me and okay. It seems my internet here is a bit unstable.
Okay. Yeah, I think I will turn off my camera so that it could like maybe it will be smooth there. Okay.
Okay, that's me.
Mm-hmm.
And let me just continue. So if we're given such conditions, and our goal is to predict the best operator for arbitrary x or for every x, and we want to bound the prediction error and also the trace error at the same time, and we found the required number of samples is a polynomial function of epsilon inverse, number of qubits, and the log inverse failure, probability failure. Here, the L infinite norm of the dense matrix is given by the maximal absolute value of the entries of the dense matrix. Also, if we relax to the target of learner ground state properties, for example, because the serial one can guarantee that the predict dense matrix is physical, it will be avoided to physical predictions. So, and then if we relax ourselves to our purpose to learn the ground state properties, it's actually given by the trace of all products of the ground states. O here is some local operator given by the summation m part summation of some local operator OI. And if we want to learn, if we just want to learn such ground state properties, and then we have another serial. So here now the training set is efficiently prepared given by xi and foxi of size a. And our goal is to predict the ground state properties given by the sigma a. Here, sigma a is in equation 1 actually predicted by the positive good kernels. And our purpose is to make it be close to the true function in terms of the prediction error. Supreme norm given by the supreme norm bounded by epsilon with probability at least 1 1/3. So here again, we bound the error for every x, not the averaged x. So in the practical science paper, they usually use the average over the parameter space, then bounded by the epsilon. So our result is a bit more strict. We for every x we bound this distance or the error to up to epsilon, and the result is the required number is about also a polynomial function of epsilon inverse and number of qubits and the log inverse delta. Further, if we assume a strong locality, that if we only learn the parted functions, and we require the for each part i's part, the function can be approximated or can be learned up to epsilon error. And now we can find the number of samples required can be reduced to logarithmic in the number of qubits. So here I just show some main rough ideas. So because we only assume the function, the target functions we are trying to learn is a continuous function. For example, the entries of dense matrix or the average of some local operators with respect to this through the positive good kernel regression. Seems a bit smooth now.
Yeah, it's kind of like it's still okay. It's still okay. Yeah, it's
okay,
a bit laggy, but we still
can
catch you. Yeah.
Thank you.
Yeah.
And yes, we try to build a model space where the positive good kernels, and here the key lambda is a PGK, and f is some function we want to learn, and through the convolution we can build for example approximator of the f is called f lambda, and this f lambda and the true values of fx have some approximation errors bounded by order epsilon. So this is the approximation of the, actually here is our hypothesis space. You can think, you can yes, we can recognize it as a hypersatisfied space or Einstein space of functions to model this target. And here because for learning process we have samples. We do not we use samples to build another discrete. We use discrete samples to build another predictors. It's called Fn. Fn means with size n to give this convolution expression as in our equation 1 actually. But here we require the kernels to be a PGK, and from Fn to F lambda we have the so-called generalization error because generalized to arbitrary x, not instantly on the training set. We build the predictor on the training set, but we want to generalize to the arbitrary x. So this generalization error up to order epsilon, and then according to the triangular inequality, we can bound the prediction error here at order of epsilon. But if we are lucky, we can find a procedure or find some techniques to with polynomial level of n, we can satisfy such a approximation scheme. So our contribution is, I think we satisfy the physical constraints of density operators, and we proposed to use PGKs, and we finally proved it's possible to use the polynomial number of samples to satisfy this triangular condition. So this is the basic summary of the main ideas for proof. And also, I think, yes, it's possible because we only assume the target to be continuous function. To compare with the existing literature, we, for example, for the task of learning ground state properties FOX, in the science paper, they assumed such FOX to have a bounded first order derivative. And then according to the mean value theorem, we can find it satisfies this relation. It actually is called the Lipschitz condition, or Lipschitz continuous actually. So it's a kind of continuous functions. And also they use the averaged or expected square norm distance in their paper to measure the prediction error. But here we use the supreme norm distance. So if we gauge the same notation, and we can find the result is given by n naught of this form. It's exponentially in the square of 1 over epsilon. If we take the 2-dimension and the parameter space, and the number of qubits is 100 and one local operator O, and 0.1 prediction error, then we can find many orders of reductions in the sample complexity. Here n is our result, and n naught is the result in the literature with different PGKs, for example, Fayer PGK and Gaussian PGK respectively. Although our rigorous results target experimentally training sets, but here we can demonstrate the theoretical findings with some exactly solvable many-body models. This allows us to test the results. For example, if we use a one-dimensional transparent field IC model, and its Hamiltonian is given by this form, and where G is the spin-spin coupling or qubit coupling, nearest qubit coupling, and H is the strength of the transverse field. And it's an important model for studying quantum many-body physics, and it's exactly solvable in dual Fermi picture. So the figure 1 plots the ground state energy as a function of the transverse field. And the red dots are exact values calculated from the, for example, the Fourier transform, Jordan-Wagner transform, and the blue stars are our predicted values from the PGK, and we use 1 million samples. It's actually here, this point. And the second figure plots the inverse prediction error versus the number of samples required in a double logarithmic scale. And so we can see a linear behavior, which indicates the sample complexity is actually a polynomial function. And note that here we also, the epsilon is the maximal error, not the average square error. Also in our paper, we proved in another perspective using the so-called reproducing kernel Hilbert space. Because we can show that the PGK predictor in our equation 1 can be is exactly one of the functions in the reproducing kernel Hilbert space, and then we can short for the reproducing kernel Hilbert space. We can short for RKHS. Then we use the RKHS and some standard machine learning theories like the radimetric complexity or generalization error bound. You can also find and verify the polynomial complexity. This is the last part of our paper, but I do not, it's a bit mathematical. I do not present here, but if someone is interested, you can refer to the paper, and there are many details there. And here we finally come to the conclusion in the paper. And we have provided the theoretical guarantee for polynomially efficient learning for quantum mathematical states and the graph properties within a class of kernel-based methods, provided that the efficient access to the training set is available and the dimensional parameter space are finite. And our key ideas and contributions to preserve the fundamental properties of the dense matrix and introducing the concept of positive good kernels. And the rigorous result indicates that the problem learning quantum manifold states and their properties can be in the framework of the PEC learnable. And this work is an exponential improvement and is an indispensable extension of the literature, and can find applications in machine learning, quantum manifold physics, quantum computation, simulation, and also in quantum chemistry. So there are two related preprints recently, and they obtained a quasi-polynomial sample complex. I think, if I recall correct, it's about 2 to polylog epsilon inverse. It's kind of a quasi-polynomial sample complexity, but yeah, they focused on learning the average of observables. But I think they assumed some kind of strong locality and with more specific models, learning models. So thank you for your attention, and questions are welcome.
Yeah, Yanming, thanks for your kind of interesting talk. And yeah, this is kind of like one of the important work that to keep us in the direction of like using machine learning to study quantum system. And yeah, as you have pointed out, like currently, I think only 4 works in this direction, right? 2 of them is this, one from you, and the other one is from the science paper, Robert Huang. So I guess there will be more work that can be done in this direction. So like for the audience, if you have any question, either you can type it up in the chat or unmute yourself to ask questions. Probably I can start off with asking one questions. So for your theorem 1, right, you assume like the ground state is a matrix of the Hamiltonian is continuous on the domain. How could we check about these conditions, like whether our program is fulfilling these conditions? Or maybe could you give examples where the dense matrix is not continuous on the domain?
Oh, you mean, yes, this is yes. If I hear clearly, that your question is how to identify whether the dense matrix is continuous or not, right?
Yeah.
So yes, yes, continuous is actually a more mathematical concept. It's hard to verify, I think, for physics. Usually for physicists, we calculate the gradient of some functions. So, I mean, from a theoretical mathematics, we calculate the gradient. I'm sorry. I usually assume for many systems it's smooth parameterized. So then we calculate the partial derivative or gradient of the density matrix. If it is upper bounded by some uniformly bounded by some constant, then it is, of course, it is continuous. If the gradient diverges, then it's usually, for example, there are phase transitions or some non-analytic behavior happens, then it will be not continuous. So because in many machine learning tasks, we first assume the target term learning is continuous function. Otherwise, if there is no non-analytic behavior happens, then, for example, if we have a phase transition to have phase A, phase B, then if we do the sampling only in phase A, then the knowledge of phase A cannot be used to predict that the properties of phase B. So this is, first, I think if we want to keep the system to be continuous density matrix, then there should be no phase transitions. For example, if we have a gapped many-body Hamiltonians, then it can be shown that the density matrix is a continuous function. Its entry is continuous function.
Right.
At least the ground state properties are the continuous. This was exactly rigorous proved in the science paper. I think I mentioned from the Caltech in the appendix in supplemental material. They proved from some bond. I think it's called the Lieb-Robson bond or Lieb. What kind of bond they can. If you are interested, you can read the details there and.
Right. Okay. Cool. Yeah, so that means like we have to be careful of the task that we want to learn, as in for your grantee is like it's kind of only valid if we want to learn the property within the same phase. And maybe like
Yes.
numerical, maybe like for theoretical concern, it would not be able to apply to the kind of predicting the kind of like property of different phases, the state of different phases. But then maybe for numerical simulations, like I remember for their work, they kind of like show that, okay, they could like even generalize to predict like the property of other state of other phases. I think there are some open questions in this direction. It would be interesting to kind of like investigate about that. Yeah. Okay.
Yes. Thank you.
Yeah. Yeah. And the other question that I have is actually you addressed like two questions of mine already. Like you already mentioned the quantum phases. Actually, I have one question for that. So for this one, you are kind of doing for ground state approximations, right? Would you be able to apply to excited state property, like to predict like the property of excited states? Like for example, excited state of the many-body Hamiltonian, like could you kind of use your theoretical grantee on those states?
You mean this
because
method
like,
to predict
because for now you assume that you kind of like predict the properties for the ground states, right? But then in, for example, quantum chemistry, like people are also like interested in the property of the first excited states. And I'm just wondering whether like your method could also be applied there or not. Yeah.
Yes, but
because because of the work that I kind of aware of, they are mostly focused on the ground states. And I'm wondering, anything can be done for the excited states.
Yes, I think there are two aspects. The first is that because it has been proved that the ground state problem can be very hard for classical algorithms without reaching out for the data, without measurement data. So that's the motivation why we use machine learning to reduce the complexity. This is the first. The second is ground states. If there is a gap and we can guarantee it's a smooth function, it's a continuous function, and it can be satisfy the learning conditions of For the exactly, yes, it's a very good question. I don't know I don't know actually. I'm not sure if the complexity of the calculating the exact states is also a very hard problem for classical algorithms. In the first part, and also if the samples or the states can be prepared efficiently for exact states, then if they can be smoothly generalized to unknown parameters or to cover the entire parameter space. This is actually, I don't know, but it's worth exploring further. It's really interesting. It's a very good question.
Yeah. Because like for the first one, I expect it to be hard to simulate classically as well, because like otherwise we can design an algorithm that predict explicit state, and then we can kind of like do something iteratively to help us to kind of predict the whole property of the system. So I kind of like expect the first one, like the excited state, to be hard to simulate classically as well, because like this is what people have faced in quantum chemistry. And for the second one, I don't know, as in for the efficient preparation of the excited state, normally I'm aware of some algorithms in like variational approach. Basically, they just like do variational algorithms and prepare the ground state, and then use that ground state and put it into cost function and trying to eliminate that ground state and trying to prepare the first excited state. So they might be something that can be done over there, but I don't know. Yeah, just some random questions. Okay, yeah. So maybe seems like maybe like the audience needs some time to think about questions. Okay, the last question maybe is kind of a bit general, because like currently we have quite a lot of work trying to prove some properties, right? What are the technique kind of like what are the standard proof technique that you think that is kind of like useful for the audience to learn? Could you kind of like mention a few? Yeah, because I guess like in your papers you kind of use a few like proof techniques, right? I think those should be kind of standard. Could you kind of like point out a bit a few, especially for me actually, I also want to learn those proof technique, like which of those would be kind of standards one that we should know?
Could you repeat? It's a bit noisy
No,
here.
because over here you like your work. I think you use a lot of proof technique to prove your results, right? I'm just
okay. You mean
wondering.
the proof details?
Yeah, no, as in like what are like, do you have any kind of like recommendations of like what kind of proof technique that we should know in order to go into this kind of this field to do some theoretical work?
Okay. You mean for students, maybe materials, reading materials.
Yeah.
I think yeah.
For me as well.
What I learned is called it's called a textbook called Foundations of Machine Learning, MIT Press. Do you know that? I mean,
yeah,
that textbook is good, and also it was written in a theoretical basis. I mean, it's not from not many applications, but it's very, because the name is Foundations, right? So and also, I mean, from a mathematical perspective, functional analysis, and because this work actually the proof for me, and it was inspired by some results in mathematics. For example, the Weierstrass approximation theorems and some results in functional analysis. So this is from the mathematics perspective. And for machine learning, I recommend the textbook Foundations of Machine Learning, and also one textbook could be written by Bishop, if I recall correctly. And yes, it's a interdisciplinary field, and for me, I think yes, I just prepared these two aspects for this work.
I see. Okay, that's cool. Yeah, like this. Yeah, I kind of like follow closely to these two books as well. Yeah, there are some technique that I also learned from this book. Okay, cool. It seems like the audience like don't maybe they need some time to think about the questions, and I guess Yanming will be happy to take any questions in the email form if you guys have
Yes.
If you guys have
yes.
any question, just like drop an email to Yanming, then
Yes, of course.
Yeah. So I guess we can like stop the seminar now, and thanks Yanming again for giving a very nice talk, and thanks for your amazing work. Yeah, so I guess we can end the seminar now. Thank you everyone. See you.
Yes, this is my email.
Okay.
You can send me. You can send both.
Cool. Yeah. See you. Bye bye.
See you. Bye bye. I just 2 emails. Okay. Thank you.
Yeah.
Bye bye.